let's say that we have some accounts, and I'm going to sneak in these accounts. The account numbers are 3 digits, so there's account 101, that's Jim, and there is Liz 202. Those are the accounts. And let's say that Jim has been doing some mining. So there's some blocks out there. And normally I do this with a whole bunch of big handouts on a board. And that is not working this year because we only have this little tiny space to work with. So this is going to be block number 84. And the reward for mining is 10. I'm going to write that up here. 10 is the reward for mining. So Jim mined this block, and in each block there is some sort of a hash that points at the previous block. I don't know what that is in this example. And there's a block number, okay? And then there is a bunch of transactions in the block. And the block has, this hash is the seal. So there's also a Merkle hash in here, okay? And that'll get calculated whatever that value is. Now, let's say that there's some other transactions in here, and he happens to get this transaction right here, that in the array of transactions, this is transaction number 2. So its position is 2. And in this transaction, okay, the previous inputs is nothing, and his output is 10. Because he got a reward of 10 for mining. Now, in a blockchain, the amount of value that you have is all your unspent outputs. So this output has no place that it goes to, so it's unspent. So he has 10. And then let's say that, forgot something already in there, the person that did this transaction to was 101. Okay, that's his account right there. Okay, so he's the one that gets the output of 10. Now, let's say that in block 85, okay, now this block has at the end of it a hash of 4010. So in block 85, we know that the previous block is 4010. It has a Merkle hash that'll get calculated as the block is built and all the things are put together. So this block points back at this one up here. Okay? So that's the chain in the blockchain. Now, blockchains are singly linked lists. Not all of them. It doesn't have to be. There's nothing saying you couldn't build one with a directed acyclic graph instead. But the new blocks point back at the old blocks. That way you can't go in and change this block without changing all the successive blocks after it and recalculating these very expensive hashes. Remember, this hash is the mining hash. It's the one that took all the time to generate, or it's the one that is been created because the person creating it has staked value to say, I will honestly create these hashes. Now let's say that Jim again, okay, he gets lucky, and over here, okay, there are some other blocks in the transactions, but in transaction 9, okay, for account 101, we have, again, no inputs because he's getting this reward as mining, and he gets 10. Now, at this point in time, we have an index, and the index is basically the locations of value. So the index has realistically 3 things in it. It has an account number, which is 101, and then it has some entries for Jim, and he may have more than just these 2, but we're going to say he only has these 2 for this example so that we keep it so we can fit it in this space. He has these 2 inputs, okay, and his inputs are in block number 84, okay, in the transaction number 2, that's that 2 right there, he has a value. So the index doesn't tell us what the data is, but it tells us where to find the non-zero unspent amounts. And then in block 85, okay, in position 9, he has another value. So the index is so we can find the amounts. Now we could keep other things in the index, but there's other information that might be associated with each one of these. Like we might want to have a memo field. The memo fields turn out to be really useful. But let's say that he says send 11 to 202. Okay? So he's going to take $11 and send that to Liz's account. And to do this, he's going to have to sign it with his private key. His public key is on chain. We can look it up. We're signing it as him as 101. So what keeps his stuff secure is the fact that he has to have the private key to do this signature. Not homework 3 or assignment 3, but assignment 4, we're going to start dealing with signatures and how they work. But right now, we'll just make the assumption that however the signature works, he signed it. It is real. It is from him. Okay, so we want to take a look at what happens when he sends 11, okay, over to Liz. Now, I've tried to make things like the block hashes here 4 digits, the amounts 2 digits, the accounts 3 digits, so hopefully you can keep all these numbers as they're flowing through separate. So this is some block later, and in this block, okay, we have, I'll put it as HH because, you know, there's blocks in between that finally point back to this block. Let's say that this block is 99. Because I just love the number 99. That's the best. Just 99, right? So, again, we're eventually going to calculate a Merkle hash when we've got all the transactions. The hash for this block will eventually get calculated down here. Okay? Just like this block eventually had a hash calculated for it. But in between, we've got a set of transactions. And this transaction is not like these mining transactions where there's no source, where there's no input. This transaction has inputs and outputs. So what we want to do is we want to take this transaction and find all of the inputs. Okay? Well, we know it's coming from 101. So we're going to go out and say, okay, for 101, I'm going to go through all the inputs and I'm going to find them. And I'm going to add up how much he has. That's one of the first steps. So we want to have a function, this is already written in your code, that gives us a sum. Okay, so the output of that function is his total, which is 20. And the first thing we want to say is, can he actually spend 11? And 11 turns out to be less than 20, so he has that much unspent outputs. And so, yeah, he can spend 11. He can send 11 off to this other person. Now, if he can't do that, we're done. So this is the first piece in the processing. Okay? Now, if he can send off 11, then the next question about all of this is, where are all the inputs to this transaction? Because I've got to find this input and this input so that I can put them in here in the input part. So the input part, okay, I'm going to put the input on this side and the output on that side. Kind of like the IO and IOHK. And we're going to say, okay, let's go find all the inputs. I need to know all the details out of the index and their values. So there's a function out there that gives you the set of inputs. Okay, and we get this set of inputs, and it's in a form that is going to be convenient, actually, to fill this in. So the set of inputs is a slice. It's an array of these inputs, okay, and we're going to say that in that array there is from 101, his account, okay, in block 84, at position 2. And from 101 in block 85 at position 9. We know his total. That's what we're using as the inputs. Now, different blockchains handle this differently. We're doing it in the fashion of when you go get the inputs, you get all the inputs all at once. So we're going to roll it up and give him change. Now, the only way he'd have change is if there's something left over. In his case, he's spending 11 out of 20, so he gets 9 back. But if he spent 20 out of 20, he wouldn't get any change. So we go and find them all. This is one way of doing it. I mean, if he had hundreds and hundreds of these things, you could make an argument that it's much more efficient to find just enough for what he's spending. That's the way Bitcoin works. Some others don't work that way. Okay, it's a choice to make. Now, those were his inputs. Now, his output, the first thing that we do is we want to create the output for this new person. So 202, we're going to have two different outputs here. And we're going to say for account 202 that, okay, the output is 11. And then we're also going to create the output for 101. That's him, his change, that his output is 9. Now, the first thing as an accountant to notice about this is that 11 plus 9 is equal to 20. I would put that check in my code that when I add those things up, I'm getting the right result. Okay, that's kind of an assertion like, oh, this has to match with that. Now, these are the pieces that go into the transaction, and we've gotten a slice of transactions, so we add the destination first, and then we append the other one later. Now, in the process of doing this, what we want to do is we want to take away his information in the index, because he spent this. This is no longer accurate. We take those away, and we say what we want to do is we want to add to the index 101, and we want to put it in block 99 that he has 9. And we want to add an entry in here for 202 in block 99 that she has, that was a value, that was the incorrect thing there, that this is at position, I don't think I wrote down the position. Let's say that it's at position 5. At position 5, he has an entry, and at position 5, she has an entry. Because we're not keeping the values, we're keeping the positions over here. So this is the change to the index. So what we do to the index is we just delete 101's things because we're adding them all up. We add new entries if there's change. If he spends all of his money and doesn't have any left, we don't have to have an entry because it's 0 in the index. And this is what's going on inside the transaction processing. Now, I'm going to go through and take this video. I'm going to go through and take this video, and I'm going to edit in pieces of what are the function calls, where are they, what order you put them in, because I did the index at the end. We don't actually do the index at the end, but I'm going to go through and actually edit this and put in the pieces of code as we're going through this and walk through the process of building assignment 3. But this is what's going on inside a blockchain. Now, I mentioned that memos are really important because every transaction has a memo field, and the memo field from mining is not very important, but the memo field down here from sending a transaction may be very important because this is where you get metadata that you can associate with this. Okay? Now, the metadata is the piece that we actually use to attach a lot of stuff to the outside world. It's not the amount that was transferred or the accounts. It is the, okay, this is the meaning that I want to have for this. When I track a cow, I may send through a 0 value transaction from myself to myself, but the metadata is the hash of the event where the cow is tracked. It's the other piece that I'm going to put on chain, and that metadata gets hashed in the Merkle hash. The Merkle hash gets included in the hash for the block when the seal is made. And consequently, it is forever marked as being real with this transaction. Now, there's other pieces, headers and stuff that go around these transactions, not just the block number, but when did it happen? Okay? And when the seal gets mined and it's actually certified that this is the actual authentic version of this, this then is permanently recorded. That permanent immutable recording of metadata, of transaction, of hash is what is in the chain. And then we move on to the next block, to the next set of transactions, and append to the end of the chain. The way this works in assignment 3 is that I'm giving you the pieces that read in the blocks, that read in the index. You're going to add to the transactions, update the index, and give me back that piece of the transaction. And then all of this stuff gets written out. So the mining occurs, it writes it. You have this piece in between to implement.